So it's my pleasure now to introduce our friend and colleague, Dr. Alan Clower. Dr. Clower is often referred to as the father of laser peening because his pioneering research and leadership in commercializing laser peening technology has left an indelible mark in the field. While Dr. Clower is officially retired from his role as chief metallurgist at LSP Technologies, he remains a valued resource and a close friend to all of us at LSP Technologies. So let's get to it. It's my pleasure to introduce to you our first speaker of the LSP 21 virtual conference, Dr. Allan Clower.
I would first like to mention that faulty vocal cords make my voice unstable. Because of this, I am narrating the slides. You will notice some variations in my voice between slides, since I could not do more than a few at a time. In this talk, I will describe how laser peening evolved from a simple experiment nearly 60 years ago to a production technology 35 years later. The development of a new technology can follow many different paths. If it directly addresses a significant problem, it may be ready for use in a relatively short time. If it is a new concept and there is no driving need, it could take much longer. Laser shocking is in this category. A relatively new technology, the first laser was constructed in 1960. The first neodymium glass laser became operational in 1961. Being new, the use of lasers in procedures and products was slow in the 60s. However, lasers were being used in a variety of experiments. One of these experiments sparked the eventual development of laser peening. As you will see, the path from a triggering event to actual use of a new technology can be long and unpredictable, and is often dependent on unforeseen or coincidental events to continue along that path. The path to laser peening can be best described as a sequence of stages or phases, each dealing with a different aspect of the journey. It begins with an idea or discovery of a phenomenon that may have some beneficial use in the future. This realization leads to investigations to better define the characteristics of the idea or phenomenon. Then, as the understanding of it grows, potential uses are suggested and further research is directed to testing these possibilities. Once the most promising use is determined, it must be introduced and marketed to the industry that can most benefit from using it. This can be the biggest hurdle. It's a solution looking for a problem that is big enough that a potential user is willing to consider taking on the costs of a process as a first user. When such a potential user comes forward, then the move to the factory floor begins. We begin in the early 1960s. The triggering event occurred in the early 1960s when two Russian scientists, Askaryan and Moroz, set out to measure the photon pressure of a pulsed laser beam on a target. What they measured was a pressure 10 to the 4th to 10 to the 5th higher than the estimated photon pressure. They suggested that what they actually measured was probably the recoil pressure from the material vaporized from the target surface by the laser beam. They also suggested that this might have useful applications. This discovery prompted many other laboratories to investigate the material dependence, magnitude, and other characteristics of the vapor impulse associated with the laser pulse. It is interesting that many of these studies were carried out at government laboratories. The U.S. laboratories had quick access to the Russian technical journals, which were immediately translated by government-funded teams. The second key event occurred in 1968. Anderholm at Sandia Laboratories was also investigating some aspects of this vapor impulse, and like all the others, the target was in a vacuum because of the high laser pulse intensities used to increase the pressures and to simplify the measurement of the impulse. Anderholm made the connection that if the vapor was confined against the surface instead of blowing off, it would greatly enhance the shock wave pressure. He vapor deposited an aluminum film on the surface of a 6 mm thick quartz disc and measured the pressure pulse with a quartz cage. His demonstration of this concept produced a 3.4 gigapascal surface pressure with a beam power density of 1.9 gigawatts per centimeter squared. The simple demonstration for dramatically increasing the impact of a laser impulse on a surface would eventually enable the development of laser shock peening. In the same year Anderholm announced his discovery, Philip Malazzi convinced Battelle it should position itself to compete for programs developing laser fusion, a hot topic at the time. This would require a large laser, and Battelle acquired a laser from France, a CGE VD640 neodymium glass laser configured to output up to 200 joules, a pulse width of 20 to 30 nanoseconds or longer, with a Gaussian beam every 8 minutes. On the left is the control station, followed by the bank of capacitors for the flash lamps. On the right is the row of amplifier rods with the output at the far end. For conducting the laser shock experiments, a small workstation was installed in line with the laser beam at the far end. With quartz overlays, the specimens were placed in line with the beam. With water overlays, in the first years, the specimens were submerged under a water layer and the beam was directed downward onto the specimen. Next, I'll discuss events in the 1970s when much of the exploratory investigation of laser processing was conducted. When it was realized that a significant shock wave could be produced in a metal surface by a laser pulse in air, it immediately generated interest in the effects it had on the target. These are the first investigations of the effect of a laser pulse-induced shock wave on the microstructure of a metal target. Merkin shocked the steel target and observed deformation twinning in the ferrite grains extending more than half a millimeter deep below the shocked area. This observation was followed by that of Metz and Schmidt, who laser shocked nickel and vanadium foils and then annealed them. After annealing, they used transmission electron microscopy to look at the microstructure in the foils. They observed small dislocation loops only in the shocked area. These could only have developed during annealing by the coalescence of vacancies produced by the plastic strain driven by the shock wave. The fourth key event occurred in 1972. After the Battelle laser became operational in 1970, in 1972, Battelle was still waiting for funding for the fusion program, and the laser physicists having the responsibility for the laser were looking for other uses for it until funding appeared. In mid-1972, Barry Ferrand approached Ben Wilcox in the Metal Science Group of Battelle as to whether there might be some tangible benefit to using laser-induced shock waves on metals. Wilcox suggested a simple experiment of laser shocking several thin aluminum alloy tensile specimens having different strength properties due to different heat treatments, and determining whether there was a resulting change in strength and ductility. This experiment resulted in the first publication of laser peening. The tensile specimens were 70-75 aluminum, 1.6 millimeters thick. They were shocked with one shot on each side with a 32 nanosecond pulse through a glass overlay and backed by a 3.2 millimeter thick brass plate. The specimens were given several different heat treatments. The solution treated in quench condition has the lowest strength because there is no precipitation hardening. After laser shocking, there is some work hardening and loss of ductility. The stronger overage condition showed a significant increase in the yield and ultimate strength with a small loss of ductility. The increase in strength occurs because the precipitates generate a significant increase in the dislocation density when laser shocked. The strongest peak gauge condition has a very fine dispersion of small precipitates between a coarser dispersion of large precipitates. This imparts a big increase in precipitate strengthening, which is higher than the strain hardening effect. Thus, the shock wave actually causes a slight loss in strength because the dislocations driven by the shock wave had cut paths through the small precipitates. This small experiment showed that a laser shock wave could significantly change the mechanical properties of a metal. Based on this result, Wilcox and Ferrand submitted a proposal to the National Science Foundation to pursue exploring the effects of laser-induced shock waves on metals. Here we see the difference in the laser shocked microstructures formed in the overaged and peak age conditions by laser shocking. These were taken at a later date than the preceding experiments. The micrographs compare the before and after laser shocking microstructures. On the left, the overage condition shows a dispersion of fine precipitates between coarser ones. During the shock wave, the dislocations are slowed down and must bow around the precipitates, creating a high density of dislocations. On the right, in the peak age condition, very fine precipitates, invisible between the coarser ones, produce the high strength. Because these very fine precipitates are so small and finely distributed, the shock-driven dislocations must cut through them. The high yield stress reflects the stress needed to push the dislocations through the precipitates, but above this stress they can move with little further resistance. Thus, fewer dislocations are formed, and the strength is actually decreased by the shock wave because it leaves behind some mobile dislocations and glide paths for movement during the subsequent tensile test. In 1974, the first patent for laser shock processing was granted to Malazzi and Ferrand. Note the broad range of pulse length and energy density covered at this time when so little was known about the process. The different characteristics of potential overlays and types of overlays is well covered. Note at that time they were also considering the possibility of using an explosive coating to increase the pressure. In the same time period of the early 70s, others were investigating the effects of laser-induced shock waves. O'Keefe and Skeen were testing how to increase the shockwave pressure with different transparent overlays and looking at shockwave interactions with thin, unsupported metal targets, among other things. Fox brought his specimens to Battelle for processing. He came up with the idea to use water and black paint, which turned out to be a very useful combination. Yang measured the pressures developed on a broad range of thin metal coatings deposited on glass overlays at low power densities, and found little difference in the pressure between the different metals or film thicknesses. In January of 1973, I returned to Battelle after spending a year at the Danish Atomic Energy Laboratory in Risø. At that same time, the National Science Foundation approved the funding for the laser shocking proposal. I was asked to take on the project jointly with Barry Ferrand, and it turned out that he and I worked very well together. This program began 6 years of support by Robert Radick, our National Science Foundation program manager. The materials effort began with a look at the distribution and intensity of the plastic strain produced by a laser shock wave. Iron 3 silicon alloy was an ideal material to do this, providing direct visual evidence of plastic strain. The physics effort began with an investigation of the pressure dependence on power density using various overlays and of the decay of the shock wave. In addition, computation of the shock waves was begun. Most of the modeling used a 1D radiation hydrodynamic code named LILA. It was originally developed by Sandia National Laboratory in 1966 and was updated by Sandia and the Air Force in 1976. Later, laser shock strengthening of weld zones in aluminum alloys and split beam shocking were explored. Near the end of the program, a 2D wave propagation code named 2D was used to determine whether the plastic strain distribution after laser shocking could be predicted. I will note here that all of the laser shots through the 1970s used a Gaussian laser pulse. Because of this, the applied power densities were generally below 4 to 5 gigawatts per centimeter squared. Above this range, there was increased reflection of the laser beam from the hotter plasma and greater risk of dielectric breakdown in the transparent overlays, limiting the peak pressure. Here we are going to look at the deformation patterns produced by laser shocking iron silicon discs. The plastic strain distribution can be seen by applying an etch pitting technique to the surface of the laser shocked cross sections of the alloy. Plastic strain occurs by the motion and multiplication of dislocations in the metal lattice. After sectioning the disc and preparing the cut surface, each dislocation appears as a dark spot on the surface. Up to about 4% strain, individual pits are distinguishable. Between 4% and 7% strain, the areas get darker, and above 10% strain, the surface again appears light. The top figure is a disc shocked with the lead plus quartz overlay. The lead overlay was initially selected and used in these initial experiments because of its low vaporization energy enabling more of the beam's energy to expand the vapor and increase the pressure. Lead worked very well for power densities between 0.5 and 1 gigawatt per centimeter squared, but its effect diminished at higher power densities. After this study, it was no longer used. Here the laser spot covered the entire surface of the discs. The deformation pattern in the upper figure shows there was significant interaction between the waves reflecting from the flat surfaces and those reflected from the circumference of the disc. The lower figure was shocked with only a quartz overlay. The etch pit distribution is similar, but much lighter than with the lead overlay. Even though the power density is almost twice that of the top figure, it is obvious that the peak pressure was lower than with the lead overlay in the above figure. Here a series of discs with decreasing thickness were all shocked with nominally the same conditions using a quartz overlay. They were shocked with a 2.5 centimeter diameter spot covering the entire surface of the discs. Although they were shocked from one side only, the back free surface shows about the same amount of strain as the front surface. There's a quartz gauge at the back surface of the two thicker discs, but not on the two thinner discs. The thinnest disc shows about 2 to 3% strain through the thickness. These are the first measurements of the decay of a laser-induced shock wave. The measurements were made on the discs of decreasing thickness shown on the previous slide. The front surface pressure measurement was made on an iron film deposited on a quartz disc. LILA was used for the decay computation. It's a hydrodynamic code and shows good agreement near the surface where most of the decay is hydrodynamic. However, deeper into the disc, where plastic work predominates, adding to the rate of decay, the measured pressure decreases more rapidly. In the left figure, we are comparing the laser pulse and the resulting pressure pulse for a water overlay on an aluminum film. The rise times are identical. The pressure pulse is about a factor of 2 longer than the laser pulse here, a little shorter than is usually observed, possibly because the power density is relatively low. The spike on the back side of the pressure pulse was perhaps the thermal front entering the quartz gauge. On the right, we see the results of using the LILA code to compute this pressure profile from a triangular pulse simulating the actual one shown in the left figure. The time scale on the right is about twice that on the left, so the actual pressure pulse on the right appears broader, but is recognizable by the ripples in the profile. The computed peak pressure is reasonably close, and the curvature at the bottom of the leading edge is also shown, but the rise time is slower. To compare the overlays being considered at the time, computations were made to gain a better understanding of how they affected the magnitude and duration of the pressure pulse. The figure on the left compares a computed profile for a zinc overlay with the measured profile. The rise time and peak pressure are in good agreement. However, the back of the measured pressure pulse decreases more rapidly than the computed one. In the figure on the right, the computed pressure profiles of iron and lead overlays were modeled with a lower power density. We saw earlier that lead outperformed iron in the etch pitting experiments at a low power density. For an input triangular pulse, like that shown in the previous slide, the two metals show quite different pressure profiles. The rise in pressure on iron occurs much further into the laser pulse than it does on lead. This can be attributed to iron requiring much more of the laser pulse's energy at the front end to generate enough vapor to increase the pressure. This results in a much shorter pressure pulse on iron than lead, even though the peak pressure is about the same. Unfortunately, these computations were expensive and time-consuming back then, or more of these comparisons would have been pursued. Holes were punched in a card for every line of code. Then drawers full of punched cards were carried to and fed into the big IBM computer. Often these computations took hours and had to be deferred to weekends. We also took a look at comparing the effects of short laser pulses to much longer laser pulses. On the left, we show a comparison between measured short and long laser pulses and the resulting pressure pulses. for a zinc and 3mm quartz overlay. Because of the longer rise time in the long pulse, the pressure peak occurs much later than in the short pulse. The 185 nanosecond pulse maintains a sustained pressure of about half the peak pressure for over 400 nanoseconds. On the right, we show short and long pressure pulses measured at the back surface of 3mm thick iron silicon discs with a quartz overlay. Here the pressure scale is in kilobars, so 10 kilobars is 1 GPa. The long pulse has sustained a much higher pressure out to at least 500 nanoseconds. The cross-section of the iron 3 silicon disc shocked with a 200 nanosecond pulse shows 3 areas of shockwave interaction deformation. These were not seen after short pulses, except when the laser spot covered the entire top surface of the disc, enabling the circumferential reflected waves to immediately interact with the axial shock wave. With the long pulse and a spot size less than half the diameter of the disc, the axial pressure was still sustained long enough that the interaction with the delayed circumferential waves, which also have a higher sustained pressure, was sufficient to cause plastic deformation. In 1975, funding was received from NASA Langley to focus on the effect of laser shocking on 2024 and 7075 aluminum alloys. This included looking at effects on mechanical properties, corrosion, stress corrosion cracking, and black paint overlays. Laser shock 2024 T351 showed increased pitting and corrosion resistance, but 7075 T651 showed little change. Both alloys displayed increased resistance to stress corrosion cracking after laser shocking, with 7075 T651 showing the greatest response. There was also an evaluation of whether the TCO2 laser could produce strong shock waves. It could not. One of the cases looked at in this program was the use of the split beam to get more uniform work hardening into flat tensile specimens. The meeting of the shock waves should increase the work hardening at mid-thickness. As expected, the work hardening was increased at mid-thickness, as shown here, and increased the average hardness through the thickness, but of course was less effective as the thickness increased. In the thinner sheet, it is clear that the average hardness through the thickness was higher than through the thicker sheet, even with the lower power density applied. In looking at work hardening of alloys by laser peening, most attention was given to 2024 aluminum. The surface hardness was measured with increasing power density to determine the pressure at which work hardening occurred. Black paint and quartz overlays were used for most of the shots. 2 heat-treated conditions were investigated. In the left figure, hardening of the 2024 T351 begins to occur at a very low peak pressure and steadily increases up to what appears to be a maximum at about 165 dph, or diamond pyramid hardness. For comparison, Herring and Olson performed flyer plate impacts on similarly aged 2024, whose hardness was very close to ours. Their flyer was a thin mylar plate producing a shock wave 150 nanoseconds long and square in shape. Their results are also plotted in the figure and slightly raise the apparent laser shock hardness plateau. For comparison, if you beat on the surface with a hammer, dph 180 is the maximum hardness of these alloys. In the right figure are the results for the stronger aged 2024 T851 heat treatment. The hardness scales of both figures are aligned here. This condition showed no work hardening from laser shocking up to a peak pressure of 5 GPa. Fortunately, Herring and Olson also did experiments on a similarly aged 2024 alloy. Their results merge with and extend the laser shock results. There is no work hardening of 2024 T851 below a shock pressure of about 7 GPa. These results demonstrated that surface hardness could be used to easily determine the minimum heat pressure to cause measurable yielding in laser shocked metals with just a series of spots of increasing intensity on a metal plate. Here we see transmission electron micrographs of two of the specimens laser shocked in the previous slide. The work-hardened 2024 T351 shows a large increase in dislocation density after laser shocking. The hardness was about 168 dph, well above the unshocked hardness of 140 dph. However, the stronger 2024 T851 on the right shows very little increase in dislocation density. Laser shocking was unable to overcome the resistance to deformation contributed by precipitation hardening from the thin, semi-coherent, lath-like S' precipitates below 7 GPa. This is the compilation of peak pressure dependence on power density gathered over the previous 4 years. The data points are the experimental measurements, and the lines are the LILA computed results. There's very good agreement. Because the measurements covered included the lower range of power density, down to 4 times 10 to the 8th gigawatts per centimeter squared, we see lower pressures from the aluminum surface than the zinc. This was attributed to its high thermal conductivity, increasing the energy lost from the expanding vapor by heat conducted into the substrate. Above 1 to 2 gigawatts per centimeter squared, this energy loss becomes small relative to the applied energy, and it aligns with the zinc and black paint data. The use of the water overlay clearly lowers the attainable peak pressure of the pressure pulse, but the tremendous advantages of applying a water overlay in practice makes it the overlay of choice for laser peening. Although it was known that water overlays produce lower pressures than quartz, there remained the question of whether there were differences in how the pressure wave developed between the two. To look at this, the relationship between the laser pulse and the resulting pressure pulse was examined for quartz and water on aluminum. The quartz overlay results are on the left and the water results are on the right. As shown here, the pressure pulse has nominally the same relationship to the laser pulse for both overlays. To get a better understanding of the observed differences between zinc and aluminum overlays at the lower power densities being used, LILA computations were made for the pressure and temperature profiles at the overlay surfaces. The same triangular laser pulse shown earlier was applied in the computations. In the figure, the two highest profiles are of zinc and the two lower profiles of aluminum. If we compare the pressure profiles, the rate of pressure increase for aluminum lags significantly behind that for zinc. There are two contributing factors. First, the surface temperature is lower for aluminum, which can be attributed to the loss of heat or energy from the vapor through the aluminum surface. Second, the delay in the pressure rise at the beginning of the pressure pulse for aluminum can be attributed to its higher heat of vaporization, consuming a significant amount of the beam energy early in the laser pulse. Because of these factors, zinc produces a higher and longer pressure pulse. In the same time period, we had a small program from the Army Research Office to determine whether pressure-induced phase changes could occur during laser shocking of some alloys. We chose the alpha phase to omega phase and the beta to omega phase transformations in titanium-vanadium alloys to investigate this possibility. These transitions were observed by others at static pressures above 9 gigapascals. To have any chance of succeeding with a shock wave, we had to increase the shock pressure above 9 gigapascals and looked at two ways to accomplish this. First, we computed what level of peak pressure we could expect from each approach. Shown on the left is the computed pressure profile for a very thin disk shocked on both sides simultaneously to develop a higher pressure at mid-thickness of the sample. Shown on the right is the computed pressure profile of a high acoustic impedance material, tungsten, placed at the back surface of the titanium-vanadium sample. These computed profiles predicted that pressures over 10 gigapascals could be achieved. However, although numerous variations were investigated experimentally, no evidence of the omega phase produced by laser shocking was found. One reason may have been that the pulses were too short to complete the transformation. In 1997, When it was becoming evident that laser shocking could be potentially useful to industry, Battelle funded an effort to expand the exploration of applying laser shocking to other materials and properties. We first examined the effect of laser shocking on fretting fatigue and fatigue of welds, with long life increases for both. The effect of laser peening on galling and wear resistance in stainless steel showed positive results. Ceramics were also investigated. Shocking silicon nitride gave interesting results with some increases in hardness and plasticity. We also had the idea to take advantage of the volume increasing tetragonal to monoclinic phase change in tension in yttria stabilized zirconia to use the tensile shock wave reflecting from the back surface to drive transformation to the higher volume phase. This would then create a compressive residual stress in the back surface and add additional toughening to this ceramic. It didn't work. Battelle also funded an extensive investigation of fatigue of 2024 T3 aluminum and the effects of variations such as the use of annular spots around holes, transparent acrylic overlays, use of momentum traps, split beam applications, and residual stress formation over a wide range of power density. We also looked at laser shocking steel in this program. In 1977, we were beginning to look at other mechanical properties beyond strength, hardening, and corrosion. Steve Ford suggested we examine how laser shocking might affect fretting fatigue in riveted joints in aircraft structures. As shown on the left, the fretting fatigue test was based on a dog bone-shaped tensile specimen with a rectangular pad clamped to it using a standard aircraft fastener tightened for 30% load transfer. When this specimen was loaded in a fatigue test, there was an elastic strain differential between the pad and the fatigue specimen due to the difference in their cross-sectional areas. This strain differential created a fretting action around the hole between the two clamp surfaces during each stress cycle. As can be seen, the results were very encouraging. After laser peening around the hole on both mating surfaces, the fatigue life was increased by at least 2 orders of magnitude at 14 ksi. During the test, fretting fatigue cracks formed on the fretted surface, but did not propagate into either the pad or the fatigue specimen. This suggested there must be compressive residual stresses in the laser shocked surface. The result became our first and primary demonstration for taking laser shock processing seriously as a metals property improvement tool. After this, we also demonstrated increased fatigue life in welded aluminum alloys by at least 10 to 100 times. None of the laser's peen specimens were tested to failure because of the length of the tests, at least 10 to the 7 cycles. At about this time, we attempted to determine whether the plastic strain distributions observed in the iron silicon discs could be computed. Computations were made using the 2D code, a 2D finite difference code based on an elastic, perfectly plastic material. The output is in isoplastic work contours, which would be proportional to the intensity of the plastic strain. Both discs shown here were given the same shock conditions with quartz overlays. The etched surface of the shock disc is shown above the computed contours of plastic strain. In the top disc, most of the deformation is near the top surface, with 4 symmetric areas below the surface showing plastic strain. However, the computed pattern predicts intense strain along the axis of the disc, both at the top and bottom surfaces, and fading radially, which is not observed. The lower disc has a guard ring press-fitted onto a disc, with the intention to produce a much different stress wave interaction. With the guard ring, the tensile waves reflected from the outer rim of the disc cannot pass back through the interface into the central disc. 2D now predicts a column of more intense deformation along the axis, as well as deformation associated with the internal interface of the guard ring. However, the most intense strain along the axis is at the top of the disc, not the bottom. The strain distribution at the guard ring interface is pretty much as predicted. Overall, where there is some agreement between the micrograph and prediction, the computation was not successful in predicting the actual strain distribution. These computations were only run through once due to the time and expense issues mentioned earlier. However, the computed results did corroborate the existence of non-uniform distribution of plastic strain observed in the discs. After obtaining the good fatigue results in fretting fatigue and aluminum alloy welds, we were funded by the Air Force to investigate laser peening around simulated fastener holes in 2024 and 7075 aluminum. The objective was to inhibit fatigue crack initiation and propagation from the holes themselves, not fretting damage. We were also to present preliminary design concepts and costs for a production laser in case of compelling results. In this program, we obtained the first residual stress measurements on laser-shocked surfaces, confirming the compressive residual stresses produced by laser peening. The fatigue results showed some improvement due to laser peening, but not enough to pursue it further. Unfortunately, we were still applying lower power densities to avoid the dielectric breakdown and reflection problems encountered at higher power densities. Here are the first residual stress profiles of laser peen surfaces. They were measured by X-ray diffraction. On the left are in-depth profiles at various distances from the hole, showing a depth of about 0.7 of a millimeter. The surface stress is at or above the yield strength of the alloy. On the right are surface measurements made before and after drilling a hole in the center of a laser-shocked spot. There was no relaxation of the tangential compressive stress after drilling the hole. Here is the first look at how laser shocking the tip of an existing crack effectively slows its propagation. This was done on 2024 T351 plate, 6 millimeters thick. As shown in the illustration on the bottom right, a central hole in the gauge section of a test specimen had notches machined into it on both sides. In one set of tests, a laser spot was applied centered on the hole, not shown in the illustration. In the other set of tests, the specimen was first fatigued a short time to initiate a short crack about 0.9 of a millimeter long, emanating from each notch. Then the tips of the cracks were laser shocked on each side of the hole, as shown in the illustration. Before testing, the crack lengths were nominally about 5.7 millimeters long, including the hole and notches. In the initial unshocked condition, the fatigue life was 1.2 to 1.4 times 10 to the 5th cycles. In the first laser peen set without pre-cracking, the fatigue life was nominally increased 6 times. In the second set, laser peening after pre-cracking, the fatigue life was increased about the same amount. Although the test started with a crack present, the laser peening extended farther out in front of the crack, contributing to this increase in fatigue life. We began looking at laser peening steel in 1980. First investigated was the hardness dependence of the residual compressive stress. In 1.5 millimeter thick steel sheet, the residual compressive stress produced in the hardest condition, Rockwell C54, was much higher than that produced in the softer condition, Rockwell C42. The surface compressive stress in RC54 steel was about the same for 1 shot and 5 shots, but in depth 5 shots produced higher stress. Because of the thinness of the sheet, more shots could not increase the depth. The zero crossing was the same for both 1 and 5 shots. It was about this time that we realized that if the front end of the Gaussian pulse was cut off to create a fast rise time in front of the laser pulse, we could reach higher peak pressures by increasing the power density. By sharpening the leading edge of the laser pulse, most of the beam energy would be quickly absorbed by the expanding vapor before the plasma progressed to reflecting too much of the beam and dielectric breakdown of the transparent overlays progressed too far. Subsequently, power densities above 5 gigawatts per centimeter squared are now routinely used. The fatigue properties were examined in 2 configurations, steel sheet and steel bar. In laser peening thin sections, where fatigue cracks generally occur at an edge, the laser peening would be applied along the edge where a crack could occur. The shock wave travels through the sheet, producing a compressive residual stress through the thickness. In this case, the compressive stress on the crack is relatively constant as it propagates into the laser peened area. On the right is shown laser peening into a notch in a beam. resembling laser peening a fillet, where the main effect is to retard crack initiation. As a crack moves into a laser peen surface on a thick section, the retardation effect decreases with depth as the compressive stress decreases. The steel was tested at a hardness of 54 Rockwell C. For the sheet tests, the laser peen spot was applied to the center of the gauge length, overlapping the ends of the side notches using quartz and black paint overlays and a split beam. In the figure, the specimens are numbered to track when the stress was increased in each test. Laser peening produced a tremendous 80% increase in fatigue strength. Laser peening the surface of the notch in the bar using black paint and water overlays, the specimens were given 1, 3, or 5 shots. With 5 shots, the fatigue strength was increased at least 30%. Tests at higher loads couldn't be completed because the loading pins were deforming the surface of the bar, so the tests were discontinued. It was clear that laser shocking was very effective in increasing the fatigue life of hardened steels. This slide shows the application of an annular laser-shocked ring around a hole. The Air Force had commented that they did not want cracks they couldn't see. When the laser peen surface surrounded the hole, a crack would form on the hole surface at mid-thickness, tunnel under the surface, and not appear on the surface until it was almost at the edge of the laser peen spot. By laser peening an annular ring some distance from the edge of the hole, the crack was immediately visible, but it was slowed when it hit the compressive stress under the laser peened ring. This still provided a factor of 2 to 3 increase in the fatigue life. This slide was presented in a talk on fatigue of laser peen 2024 aluminum in Los Angeles in January 1983. I thought this would be my last talk on laser shocking. It could be years before the right circumstances created new interest in pursuing laser shock peening. By the early 1980s, it was getting more difficult to get funding for laser shock investigations. It was no longer a novelty, and the broad outline of the effect of laser shocking on metals had been sketched out. The research funding sources felt that it was no longer an appropriate use for basic research funding. It was time to identify potential users of the technology and sell them on funding the work necessary to have a technology they could use. Key Event 5 was initiated within a week or two after the Los Angeles conference, when I received a call from the foundry manager of a cast iron foundry in Decatur, Illinois. He had attended the talk in Los Angeles. The foundry was Wagner Castings, making castings for the auto industry. He visited Battelle, saying there had been recently a management buyout of the foundry from the Wagner family, and the management was now looking for ways to broaden their market. When he had reported on the Los Angeles meeting to management, he described laser shocking as something they should consider. The idea was that if they could improve the fatigue properties of laser peen cast iron to match that of steel, they might be able to undercut the price of steel parts and capture a share of the market. When I visited Wagner Castings the next week, they agreed to fund laser peening of cast iron test specimens and test them. If successful, they would negotiate a laser peening license from Battelle and support development of laser peening at Battelle for their use. To demonstrate fatigue life improvement of laser peened iron castings, tests were run on small as-cast tensile fatigue specimens laser peened into the notches on each side of the specimen as shown in the illustration on the right. The cast iron shown here is ferritic malleable cast iron. Laser peening produced a 60% increase in fatigue strength. The other types of cast iron also showed increases. After these tests, Wagner negotiated a licensing agreement with Battelle and commenced to fund the development of laser peening. Not long after this, Wagner thought another way to broaden their market would be to remake themselves into a near-net or net-shaped part provider by acquiring a company that produced powdered metal parts. They would then laser peen them and expand their market. To assess whether laser peening could significantly improve the fatigue strength of powdered metal parts, Wagner supplied notched powder metal tensile fatigue specimens identical to the cast iron specimens. They were a typical iron-powdered metal product consisting of pressed and sintered automotive-grade iron-nickel-carbon powder sintered to 89% density, so plenty of porosity. On the left is the surface compressive residual stress measured on one edge of the tensile specimens as shown in the drawing. The best fit to the data was with cumulative energy, that is, the sum of the energies of all the shots placed in one spot. 4 different energy densities were applied, accumulating up to 5 shots on one spot. The 22 joules per square centimeter shots produced no compressive stress on the surface, but the 42 joules per centimeter squared and higher shots did. Even after shots of 80 joules per square centimeter, the surface residual stress is still decreasing linearly, that is, more compressive. On the right are the fatigue results. The laser peening was directly into the notches on each side of the specimens. The fatigue life improved dramatically with increasing shots. 5 shots at 100 joules per square centimeter energy density produced an increase of more than 2 orders of magnitude in fatigue life. However, their deal for a powder metal company did not work out. In 1986, Dr. Remy Febreau and Jean Fourier from the École Polytechnique in Paris visited Battelle to discuss laser shock processing. After returning to France, Dr. Febreau's group initiated an era of extensive work on many important aspects of laser shock processing in France in the following decades. This work was of great benefit not only to our activities, but also to providing information and encouragement to other groups interested in pursuing the technology. All these combined efforts have contributed to the increasing acceptance and use of this technology over the last 30 years. For Wagner to demonstrate the commercial feasibility of laser peening, they would need a laser with a small footprint and a pulse rate much greater than 1 every 8 minutes. By 1986, Wagner made the decision to fund the design and construction of a small footprint laser providing 2 beams of 50 joules each, 20 nanoseconds, with a 1 Hz pulse rate. The laser was designed by Harold Epstein and built at Battelle. This prototype laser demonstrated the feasibility of future commercial use of laser peening and was to be used for future process and applications development activities at Battelle. The laser is shown on the left with the capacitors and control panel in the cabinets behind the table. On the right is the plexiglass enclosed workstation. In 1986, Jeff Delaney joined Battelle and led the laser physics team. The next step was to take the technology into the marketplace, a solution looking for a problem. In the late 1980s, after building the prototype laser was underway, Wagner and Battelle began to market the technology. Wagner's plan was to provide laser peening services as well as using it in their foundry. Laser peening was largely unknown in the industry. John Kuski, Wagner's chief engineer and LSP program manager, assisted by me from Battelle, undertook to introduce industry to the new technology and develop interest. From the many presentations and phone calls made to companies who could have a perceived need for laser peening, numerous test parts were given to us to laser peen and returned to the companies for testing. In most cases, there was significant improvement in fatigue life. However, we weren't equipped to immediately offer services. There was no laser peening facility. It was difficult to convince a company that great test results on their product justified a future commitment to install or send their products to a non-existent facility. However, we were accumulating valuable laser processing experience and data that would be useful in that transition later. I was told that it was much easier to introduce a new alloy or material to industry than a new manufacturing process. A new process had to fit into an existing manufacturing system with minimal interruption of the flow of product. However, if there is a crisis with a product and a new technology was a solution to the problem, there was a huge incentive to get the new technology into the product, despite the cost and inconvenience of doing so. The situation was about to change. The sixth key event occurred at a presentation made by Kuski and myself to the Air Force at Wright-Patterson Air Force Base in Dayton, Ohio in 1990. After the presentation, William Cowie asked whether we had talked to General Electric aircraft engines in Cincinnati. We said we hadn't been able to set up a meeting. He took us to his office, got on the phone, and set up a meeting with them for us later in the week. At the meeting, after an abbreviated presentation on laser peening and much discussion, GEAE gave us their small standardized test piece to laser peen and returned for evaluation. The problem was that the F-101 engines on the B-1 bombers were susceptible to foreign object damage on the leading edge of the first stage fan blades. Damaged blades could fail in flight and destroy the engine. It was possible that the engines were sucking in fine particles from the runways on takeoffs and landings, since most of the damage were small nicks a few tenths of a millimeter deep. These small nicks could not be tolerated. During inspections, they were detected by dragging a thread or thumbnail along the leading edge. If a nick was detected, the blade had to be replaced. Though small, they imposed a huge operational cost for damage detection and blade replacement, as well as grounding the planes waiting to be repaired. After evaluating the laser peen test piece, GEAE sent 4 first-stage fan blades for laser peening. They were to be laser peened along the leading edge up from the platform. When the 4 laser peen blades were returned to GEAE for testing, they damaged them many times more severely than a nick. They used a hacksaw to make a 6 millimeter deep notch in the leading edge. After testing them, the results were almost unbelievable. They tested like new blades. There was no need to pursue optimization of the processing parameters. With this result, further testing and planning for implementing the process on the blades began. Years later, the Air Force did their own evaluation of the process. These are their results. The Air Force compared damaged blades given different surface treatments and 2 different types of damage to a new blade. The surface treatment conditions were dual shot peening applied to new blades at that time, high intensity shot peening, and laser peening. The 2 types of damage were a sharp chisel pushed 6 millimeters into the leading edge and a 3 millimeter deep cut by electrical discharge machining. The chisel damage had heavy plastic deformation at the notch tip, while the EDM notch had none, but instead had a thin re-solidified layer, probably containing small shrinkage cracks with some tensile residual stress. The blades were tested on a siren testing device at a very high frequency after being held 24 hours at 400 degrees Fahrenheit. The testing began at a stress amplitude of 20 ksi, then stepping up the stress by 10 ksi increments at 1 million cycle intervals until failure. The new blade test is on the far left. The baseline damage test had a very low life. The high-intensity shot peening showed a slight improvement over the dual peen condition, but still had much reduced fatigue strength after being damaged. By contrast, the damaged laser peen blades had a fatigue strength higher than the undamaged blades with the chisel notch and about the same as the undamaged blades for the EDM notch. This result was due to compressive stresses being high enough through the thickness of the blade for some distance from the leading edge. The compensating tensile stress was at the rear of the laser peen patch, well away from the leading edge. Therefore, any incipient crack in the leading edge was clamped closed and unable to grow. The early 1990s were a time of transitions. In 1987, Wagner Castings decided to become part of a holding company, Sudbury Incorporated. Soon after that, Sudbury began to run into financial problems, leading to bankruptcy in 1993. At that point, Wagner was told by Sudbury to return the laser peening license to Battelle and cease supporting any further development. The impact extended farther than Battelle, however. GEAE had an agreement with the Air Force to begin laser peening of in-service F-101 blades in 1997. Wagner was to build a laser peening facility and be prepared to process the blades at that time. With Wagner out of the picture, GE had to change plans. In early 1994, Jeff Delaney began negotiating with Battelle to acquire a license and start his own company. Jeff Delaney founded LSP Technologies in February 1995, operating out of quarters in the basement of Battelle, and received a license for laser peening from Battelle in the summer of 1995. At the same time, GEAE also negotiated a license with Battelle and asked Delaney to help them evaluate the laser manufacturing company's capabilities to build production lasers in the short time available. They decided that none of them could. Failing to find a suitable commercially available laser, Delaney offered to design and build the lasers for GEAE under their supervision in the summer of 1995. Todd Rockstraw led the GEAE team. I retired from Battelle in December of 1994 and joined LSP Technologies in September 1995. Chris Likens of the Air Force Materials Laboratory provided significant funding to continue to pursue laser peening programs at LSP Technologies. LSP Technologies delivered a small laser to GEAE in 1996 to begin low-volume production. When the first production laser was delivered in 1997, they went into full production. 2 additional lasers were delivered later. Finally, 25 years after Wilcox and Ferrand performed the first experiment of a laser-induced shock wave increasing the strength of 7075 aluminum, laser peening achieved the status of a commercial production process, providing a huge advance in the operational safety and maintenance cost of an aircraft. With that benchmark achieved, Air Force support was now key to keep the technology growing and advancing to address lowering cost and increasing the number of users and applications. To ensure that the technology would be available to it and its suppliers industry-wide in the future, the Air Force recognized it needed to nurture the development of a strong business foundation for the technology. Then, at some point in the near future, industry itself would be driving growth and advances in the technology, and it would be there for the Air Force to use if needed. To help achieve this goal, the Air Force Materials and Manufacturing Directorate funded the design and construction of a production prototype laser, a production laser and work cells at LSP Technologies. These lasers were used extensively for production and development. In another step forward, they have now been replaced by lasers with advanced design and capabilities without outside funding. With these Mantech-funded lasers, in 2003, LSP Technologies began production laser peening the blades of an integrally bladed rotor for the F-119 engine built by Pratt & Whitney. The F-119 engine powers the F-22 fighter aircraft. In the late 1990s, Dr. Yuji Sano introduced the use of low-energy lasers for laser peening welds in nuclear reactor vessels. Applying laser pulses of about 100 to 200 millijoules onto spots less than 1 millimeter diameter at a high pulse rate, he attained compressive stress depths of up to 1 millimeter by applying thousands of spots per centimeter squared in multiple layers. Features of the laser peening without coating, or LPWC process, are that it does not use an opaque overlay. It can be used underwater at a large standoff distance by having the neodymium glass wavelength to 532 nanometers. It can be modified to deliver the beam through an optical fiber and is relatively portable. The last 20 years have seen much increased activity in laser peening around the world. Shown here is a list of countries that either have or have had laser peening programs. They are listed in the order of the year of their first publication. There are 25 countries listed. I may have a few wrong, but it demonstrates the widespread interest and the increase in the rate of laser peening knowledge now being generated worldwide. A total of over 1,000 technical papers have been published on laser shock processing. By far the most address laser peening. I first showed this slide 9 years ago and updated it by adding data for 2021. The chart shows the growth in active patents and applications worldwide since 1974, when the original patent was granted. Most of the observed drop in the U.S. patents since 2012 is due to the expiration of patents applied for before the year 2000, with few new patents being applied for. However, there has been great growth in Asian patents since 2020. Most of these are in China. The eventual success of laser peening as an industrial process was not only dependent on the unexpected turn of events and coincidental timing of other events, but equally dependent on the many dedicated contributors to the success of laser peening. There are too many to list everyone, but I will name a few. Barry Ferrand, John Kuski, Jeff Delaney, Robert Renick of the National Science Foundation, laser peening's champions in the Air Force Wright Laboratories, Bill Cowie, David C., Otha Davenport, Chris Likens, laser peening's champions in GE aircraft engines, Todd Rockstraw, Manny Manava, the French contributors, Rene Fabreau, Patrice Père, Laurent Bertha, then Yuji Sano, Jose Ocaña, and many others. Almost 50 years have passed since Barry Ferrand asked Ben Wilcox whether a laser-induced shock might have some useful effect on metals. Little could they have envisioned the impact that conversation would have in the future. They took that first step on the path to an entirely new technology for making metal surfaces much more resistant to fatigue failure than existing technologies. It has been a privilege to have traveled on this path along with the many others who have made critical contributions to the definition and growth of laser shock peening. To all of you who are taking this path forward, the future is in good hands.